Well, like, it looks like almost as good as like, it's like.
So bad.
I think a big.
Okay, guys, today we're just going to practice what we did yesterday. And I am going to introduce the limit definition, the alternate limit definition, but it's the same concept. Taking the concept of slope, attaching limit to it to allow for us to not only find a slope between 2 points, but working towards finding slope at just requiring just 1 point. And that gives us that flexibility to be able to find an exact steepness of a curve at a point. We did number 3 in your packet. Let me just run through those steps again, and then we'll try number 4. Talk about the alternative definition, and then we're just going to work through page 5 and 6. Okay, so in class we'll do page 5 and 6. Your assignment for next Tuesday will be pages 7 and 8, which is just basically the same thing, just additional practice. The key is attached. And then on Wednesday, I'm going to be checking your packet, make sure, show me that you worked through all the pages, as well as the homework from the textbook. Okay. And so I will send out a reminder for you Monday and Tuesday to let you know that I'll be checking those things Wednesday in class. And then starting Wednesday, we're going to really start chapter 2, and we're going to learn power rule, and that is really where the foundation of this semester is going to begin, 2.2. So everything we learn from 2.2 on, we're going to use all the way to the end of the semester, even until the end of the school year. So, but this is really just a setup to help us see that derivative is just a fancy word for slope, and we're just basically working with slope to arrive at our slope formula, our derivative equation. So we talked about how we're trying to adapt our function into this specific derivative formula, and we understood that this looks complicated, but really it's just y2 minus y1 over x2 minus x1, and the denominator cleaned up a little bit, so you're not seeing that x2 minus x1 quite the way that you're expecting, but you know it's coming from the slope formula. So we want to make our substitutions, right? F of x gets replaced with square root of x, but we need to make sure that we build out our functions so that we know where to put that x plus h. So here's a foolproof way to do it without making a mistake, but you do need to take an extra step. So given the function, you rewrite the function, but you remove the x, but then you reserve a space using parentheses where the x was. So if you can go from this step to this step, you're not going to make a mistake because there's only one place that the x plus h can go, and that's inside these parentheses. So for every x that you remove, you're going to have an empty parentheses, and then you're going to fill those parentheses with x plus h. And now we know exactly what to replace. F of x plus h gets replaced with the square root of x plus h. And we are this essentially is the limit definition of a derivative. But when we make those substitutions, we're just basically treating it like a limit problem. Okay. So we insert 0 into the expression, we get 0 over 0. Remember, you're replacing the h with 0, not x. Okay, it's the h that's moving, not x. So replacing the h with 0, we get 0 over 0. We know that this is a conjugate problem, so we identify the conjugate, multiply. We FOIL and expand out the numerator, but we leave the denominator alone. And when we expand out, we're always looking for the same thing every time. We're looking for an h that we can isolate in the numerator, because that's always going to be the cause of your whole. So you're always going to cancel out your h's after you clean everything up. And once your h goes away, in this case, there's a 1 left over in the numerator. You reevaluate the limit, and we get 1 over root x plus root x, which is 1 over 2 root x. And 1 over 2 root x is going to be a slope formula designed specifically for this function y equals square root of x. So once we have a function in its derivative, we can create these tangent line equations for any point on the curve. So part B was find the equation of the tangent line at x equals 2. We insert 2 into the function to get the y value. We insert 2 into the derivative to get our slope. Once we have our order pair and our slope, we can write our tangent line equation. Okay. We're going to be asked to do the tangent line equation a lot. So each time we learn a new derivative rule, we're going to go through this process. Okay. So you're going to do it so many times that it's going to become second nature in terms of the amount of times that we are going to see it this semester. Okay, any questions with 3? Okay, so now let's look at number 4. Now, number 4 is this alternate or this alternative definition, and that was on page 1. I briefly just mentioned it, but we're going to be working with this alternative definition now. It's going to do the same thing. It's going to find the slope of a point on the graph, but it's also a little bit different because with the original general limit definition of a derivative, it's a two-step process. We find a slope formula, and once we have that slope formula, we can insert any x value to get the slope. What the alternative definition is going to do is going to take us directly to the numeric slope. It's going to bypass the slope formula, and it's just going to go directly to the slope value that we're looking for. Yes.
Do we have to memorize these ones?
No. I think down the road we may bring this back, but I'm just going to, yeah, I think I'm just going to go over it a couple of times, and then we're going to move on to 2.2. You know, this is a topic that AP exam does technically is on the list of things that we need to know for the AP exam, but the amount of times that it shows up is minimal, and we also have a workaround for these definitions using L'Hopital's rule later on. So I think for now we don't have to worry about memorizing it just yet. But if we do, I'll let you know. But right now, I don't think we do. Okay. All right. So let's go to number 4. And let's talk about working with this alternate definition. So number 4 in your packet. This is going to be page 3. Okay. So number 4, it says use the alternative definition to find the slope . So let me write out the limit definition here. What I appreciate about this limit definition of a derivative is that we can more easily see that connection with slope, right? You look at this f of x minus f of c, and this instantly reminds you of the slope formula. It's a little bit harder to see with the general definition, but here we see it. It's more apparent, right, that the derivative is basically just a way of reworking the slope formula. Okay, so the first thing that we do is, it looks like there's a lot going on here, but we'll break it up into steps. The first thing we do is we want to replace our c value. Okay? So I'm going to underline all the c's here. What do you think the c value is? 2. Yeah, that's the center of our problem. That's our C value. So let's go ahead and do that. Rewrite the entire problem and replace your C value with 2. Okay. Things are beginning to take shape. Less variables makes it easier to kind of decipher what's going on. Now, just like with the general definition, we're going to be making substitutions with the numerator. Okay. So what do you think we can replace with f of x? Square root of x, that's an easy substitution. Okay. What do you think we can replace with f of 2? Right. So all we do is, this is just the y value of the function. So it's a little bit easier than the general definition because we don't have to worry about this f of x plus h and students messing up what to do with that x plus h. This feels a little bit easier. Since our f of x is square root of x, f of 2 is just square root of 2. Okay, we're just finding the y value of the function. Okay. So let's set up our numerator now. We're going to be able to get the numerator out of function notation and into something that we can work with algebraically. Okay, so now this just turns into a limit problem that we imagine can see in the first unit. First step is plug in 2, right? And what do we get? 0 over 0. We know there's a hole. We know there's a limit waiting for us. We just have to find it. So multiply by, this is a conjugate problem, right? Okay. Just like with all the conjugate problems that we've seen, we're going to expand the numerator, but leave the denominator alone. And if you look at your original limit problem, you see there's an x minus 2 in the denominator, and that's giving you a hint as to what you want to show up in the numerator. You want an x minus 2 to show up because that's what's causing the hole. Pull everything out. All right, what do you see in the numerator? Cancels out. Okay. Do you see something clean that we can remove? X minus 2. So that's what we want, right? We knew at the very beginning that we're trying to find some version of x minus 2 to show up because we see that in the denominator. Okay, what's left in the numerator? 1. Okay, now what's the last step here? Good. Plug in the 2 limits for x. Now it's a little bit different from the limit definition, right? The general definition, we're changing out the h's, but here we're changing out the x. Okay. And what do we get? 1 over 2 root 2. Now look at example 3 versus example 4. It's the same function, same derivative. We just went through a slightly different path. The general definition is going to first stop at a slope formula, and then we take an additional step to find the slope. Here, the limit definition is going to bypass the formula and take us directly to the slope value. Okay, I'll talk about that definition differentiability Wednesday when we return. But we've seen everything that I want us to see for 2.1, so we're just going to practice the general definition as well as the alternative definition, and then understanding that, how to find order pair, how to find slope, and also equation of tangent lines. So which is going to practice through that for the rest of the class today, and then have you guys do it for Tuesday for your for the virtual day assignment. Okay, so page 5. And before I forget, for number 2, if you guys can make that adjustment, find f prime of 2, f of x is square root of 3 minus x. The 2 minus x is not going to work. It's not at a point that is favorable for finding slope. So before I forget, you guys can make that change. Okay. All right, we're going to step through number 1. If you want to work ahead, you're welcome to. The key is attached at the back of your package. Okay, so we're going to start off with the limit definition, the general definition. We work on a separate sheet, just like my one row. Okay, so let's see if we can make our substitutions, right? We know what f of x is going to be replaced with, but let's work on creating the space so that we can build our f of x plus h correctly. So off to the side, here's my function. I'm going to rewrite my function and replace all the x's with a set of parentheses because I am saving that space for my new argument to help me build my f of x plus h. So now if we do this, we're not going to make a mistake because there's only one place that we can put the x plus h, and it's inside those parentheses. All right, so now we can start building our limit definition. So now I have a perfect replacement for f of x plus h. It's this entire expression here. Okay, I see a lot of students leave that there and they start working on the denominator, but what else do we need to include? We need the f of x. Okay, and now there's also something else that we got to be careful about. What do we have to be careful about when we put that f of x down? In set of parentheses. There are multiple terms in that f of x. If you don't have a set of parentheses, you're not going to be able to get this to work out. Your numerator is not going to clean up the way that you would like. Okay, I know that this process is tedious, but we just have to, kind of bear through this today and Tuesday. When we get to Wednesday, we're gonna have a much more efficient way. And when you get to Wednesday, you're gonna be like, wow, this is so much easier with this new method. Why do we do this? Well, we do this because we really want to make sure that we understand that this slope, this derivative is really coming from slope, right? And then seeing this f of x plus h minus f of x all over h is really a reminder that derivative is just a reworking of slope, a fancy way of representing slope. Once we learn power rule next Wednesday, a lot of this field will become more abstract. So we'll want to really kind of help students understand that we're dealing with slope, and that's really the concept that's going to carry us through the rest of the semester. Okay, so first things first, right? Now this becomes a limit problem that we can do algebraically. Replace all the h's with 0. And we're gonna get 2x squared minus 3x plus 1 minus 2x squared plus 3x minus 1. Everything will go away in the numerator. We're left with 0 over 0. So we know there's a hole. We know there's a limit waiting for us. And we just have to clean up all that numerator. Now, what's the appropriate way to clean up that 2x plus h squared?
Foil and.
Good. Foil and then distribute, right? If you distribute the 2 through first and then expand, we got to make sure we follow order of operations, right? Exponents is going to be handled first, and then the 2 can be handled. I know that's easy. It's easy to make that mistake because we want to read from left to right. We want to do whatever we see first, but we really need to handle the foiling out first. Okay, continue cleaning up. All right, a lot of things should pair up and go away here. Okay. If we do this correctly, we should be able to factor what out of every term? H, yeah. We're guaranteed to be able to cancel an H out. So if you have a term at this point where something is not left with an H, then something went wrong, okay? Then we missed something. We have to go back and check because at this point, we should be able to factor an H out of every term. Okay, so first term, if I take an H out, I'm left with 4x plus 2h minus 3. Okay, just like what we wanted. H's go away. What's our final step? Replace every other remaining H with what? 0. So now things will clean up. We should be able to get it down to just in terms of x. So this 4x minus 3 is the slope formula for this original curve, 2x squared minus 3x plus 1. So this is tailor-made for our function. And what this does is any x value you plug in, it'll give you a number. And that number is going to tell you how steep that point is on this particular graph. Okay, any question with 1? Okay, all right, number 2. This will be the, now we're doing the alternative definition for a different function. And with the alternative definition, it's always going to be at a point. So you're, it's always asking for a slope, a numeric value. Does anybody still need to look at number 1? All right, let me write out the alternative definition. Okay, what's the first thing that we can do?
Okay.
Plug in, yeah, plug in the C, replace all the C values, right? Let's get that piece out of the way. Makes it a little bit easier to figure out what to do next. The numerator, we're always gonna have to make some substitution for the numerator. F of x can be replaced with. Oh, yeah, make sure that you guys change it. Yeah, so, I made a mistake on that, on your, handout. I forgot to change it. So if you can change it to √3 minus x. Right, and then what can I replace with that one too? So, yep, we just want to find the y value of the function. So 2 in for x, √3 minus 2 is same thing as what? Which is just 1, right? √1 is just 1, okay? So we're always going to substitute the numerator and leave the denominator alone because denominator is always going to be ready for our algebraic step. Okay, so now we're just doing a limit problem algebraically. First things first, insert the 2. We'll get 1 minus 1 over 2 minus 2. Okay, conjugate method. All right, go ahead and FOIL. Okay, the radical goes away nicely. And we're hoping for some version of an x minus 2 to show up in the numerator so that we can cancel that out with the denominator. Do we see that or some version of it show up? Is it a perfect fit? It's close, right? Okay, what adjustment can we make so that we can get those two to pair up?
Yeah.
Yeah, they got -1. So. Okay, remove the cause of the whole, reevaluate the limits. So again, with the alternative definition, it's just going to take you directly to a numeric slope. What's our slope value? -1 over 2. So it's telling us that whatever this graph square root of 3 minus x looks like, at 2 on the graph, there's going to be a very gradual negative slope of -1/2. Giving us very detailed information about how the steepness of the graph looks at that point. Yep.
Step down, we put the 1 in for f of 2. For the for 3 minus x, why do we do -1 to the +1?
Oh, okay. Like this, you mean?
No,
Like square root of 1.
down here on the other, where like the red is.
Uh-huh.
So why are they not flip-flop? Like, why is the X on the other side, why is it not positive? And those are negative.
Good. So when we do conjugate method, we only make one change. We only change the sign between the terms.
Okay.
We don't change anything with.
Well, I'm saying, why is the one on the left negative?
Oh, with this one here?
No, the one next to the blue. Why is that -1? Why is it -1?
Why is it -1? Okay. Oh, because f of 2 is 1, and my formula is f of x minus f of 2. Yeah.
Thank you.
That's fine, yeah. Yeah, there's so much going on, so, yeah, feel free to ask any questions because, yeah, understand, you know, when you're doing 50 things at once, it's hard to keep track of everything. Okay, any questions so far? All right, good. So, we saw limit definition, we did the alternative definition, and now, number 3. Let's do a limit definition again, okay? So try number 3. Go through the steps. I'm gonna have you guys try on your own, but I'll work through it at the same time that you guys are trying it. So let's go back to the original definition, the h approaching 0. Oh, that's my bad. Okay, everybody set up, look good so far? Now, once you FOIL out the numerator, again, what do we have to be careful about with that last term? Okay, parentheses, negative parentheses, right? Because once the radical drops out, then the negative is going to be able to distribute through the parentheses or through those multiple terms. We want to make sure that we have that showing. If we don't, then it's not going to clean up the way we want it to. Oh, I missed something. The denominator needs to have this as well. The H's cancels out cleanly. There's still that 2 left up top. Once we remove the whole, we can reevaluate the limits, replace any remaining H's with 0, see what's left over. So again, this derivative, the purpose of this derivative function is that it's going to allow us to figure out any slope that I want on the original function. I can give it an x value, it'll give me a number, and that number will correspond to how steep that point is on the graph, on the original graph. Okay, just 2 more. We're gonna get through page 6, numbers 4 and 5. Again, we're gonna use the general limit definition for number 4. But it's gonna be a 2-step process. We're going to find the derivative function first, f prime first, and then we can insert the 3 into the derivative function and get the slope value. So, yeah, 2-step process. All right, does anybody still need this on the board? go ahead and rewrite your function using parentheses so that you know exactly where to put that x plus h. Yes, question? Oh, hold on, let me see. Yeah, sorry, I on the key, I put the page 7 and 8 first. And so I switched it up, but it looks different. Yeah. Okay, right, so x plus h. So now we have a perfect substitution for f of x plus h. I'm going to go ahead and distribute the negative through. Okay, replace all the h's with 0. We get 2 over 5 minus x minus 2 over 5 minus x. That's 0. 0 over 0. This is a common denominator complex fraction problem. So I'm going to spend the time to get that common denominator between these two fractions. Guys, if you get to number 5 before I do, we're going to do the alternate definition. We'll get a practice in with the alternate definition with the next problem. Okay, balance each fraction. Okay, a lot of things cleaned up nicely. But make sure you bring it back to the original problem, right? There's still this h that we got to deal with. So we're hoping that these two h's will find its way to cancel out. I'm going to bring this denominator h up. Multiply by the reciprocal. H pairs up nicely and goes away. Place the remaining h with 0. Now that we have our slope formula, our derivative, we can figure out the steepness of this graph at 3. So now we can plug 3 into the derivative and find the slope of the graph at that point. Sorry, 3, I don't know why I put it to 3. Okay, I didn't quite get to number 5 with the alternative definition. So finish this up and do page 7 and 8 for next Tuesday and complete the assignment in your textbook. Okay. Okay, come up and get your phones.